Today we're going to look at the binary search tree and the binary search tree's basic methods. These methods include find recursively, insert, remove, get successor, soft delete, get the smallest value in the tree, get the largest value in the tree, Inorder Traversal, Preorder Traversal, Postorder Traversal, get the number of leaf nodes in the tree, and get the height of the tree. So what is a tree? A tree is a collection of nodes that have references to other nodes. What is a binary tree? A binary tree is a collection of nodes where each node has a reference to only two other nodes. Typically, we don't use a regular binary tree. We usually use a binary search tree instead. So what's the difference between a binary tree and a binary search tree? In the binary search tree, the left node is less than the parent node, and the right node is greater than the parent node. Also, a binary search tree is a logical structure or an abstract data type, so it can be implemented in many different ways. Binary trees can also be balanced or unbalanced. For example, if we had a bunch of right nodes attached to the tree instead of left and right nodes evenly distributed on the tree. To calculate the height of the tree, we can find that the tree is 2 to the power of h minus 1 equals n, or h, the height of the tree, equals to log of n plus 1. And this means that the height of the tree is big O of log n, base 2. Also, each section of the tree is a level, starting at level 0, and then level 1, and then we go to level 2, and so on. The time complexity for many operations on the binary search tree are very similar. They're usually big O of log n base 2 when the tree is balanced. So the find operation is big O of log n base 2. The time complexity for delete and insert are also big O of log of n base 2 because they're essentially finding the nodes and then performing a constant time operation to either insert a new node or to remove one of the nodes. Some data structures in different languages that use binary search tree in their implementation are in C#, there's the sorted dictionary, in Java, there's the tree map, and in C++, there's a set class. Also, it is important to note that the heap is an implementation of the binary search tree. So let's look at the basic structure of a binary tree before we go through the methods. So here's our binary tree class. The binary tree has one property, that is the root node. It is of type tree node. A tree node is simply a node class that has a data property to store the node's data. When actually coding, this data could be a key and object pair that's unique, but in this example we're going to use integers for simplification. Each tree node has a reference to another node called the right node or the right child node. This node is greater than the current node. Each tree node also has a reference to a left node, which is less than the current node. Each tree node can also have a property is deleted to signify a soft deletion of the node, which is simply a boolean saying if this current node is deleted or not. Here we have our node constructor, which simply takes in a value and sets it to the data of this node. Then our node has some internal methods that line up with the binary tree that we'll look at later. So now we're looking at our main method in our program class, which is the starting point of this application. First, we instantiate the binary tree. The first method that we're going to call is the insert method, and we're going to insert all of the following numbers. So let's start this program and step through. Okay, we're going to start with inserting 75, and now we're in the binary tree class, and we're looking at the insert method, which is taking in some data. If the root of the tree is not null, then we need to call insert on the root node. In the first case of inserting 75, the root is null at this point, so we need to set the root node to be a new node with the data of 75 inside of it. So we hit our constructor and we set the value to the data of the node. Next we insert 57. Since our root is not null, now we need to call insert on the root. So we're passing in 57 to the insert method of the tree node class. So now we're in the tree node class and we're looking at our insert method on the tree node class. This method recursively calls insert down the tree until it finds an open spot on the tree. So if the value passed in is greater than or equal to the data of the current node, then it's inserted to the right of that node. And so this value is 57, and our root node is 75, so 57 is less than 75. So we drop down here. Since the data is less than our current node, we are trying to insert it as the left node, but we need to check to see if the left node is null or not. In this case, the left node is null, so we simply set the left node equal to a new node with the value of 57. Next we're going to insert 90, which is greater than 75, so it'll be going to our right node. Call the insert method. We'll call insert on root. And here our value is greater than our data, so 90 is greater than 75. So we're looking at the right node. The right node is currently null, so we simply set the right node in this case. So the right node we set to a new node that is equal to 90, the value that we passed in. Now let's insert 32. 32 is less than 75 and less than 57, so it should be the left node of 57. So we call our insert method, which calls the insert method on the root. 32 is less than 75, so now we are trying to insert it at the left node. We check if our left node is null, which it is not, and so we call insert on the left node itself. So the left node is the node that we previously inserted, 57, and we're calling insert on 57 now with the value of 32. So this recursively calls this method, insert, comes through again. Now it's comparing with 57. Are we greater than or are we equal to 57? We are less than 57, so we go down to the else statement. And now our left node of the current node, which is 57, is equal to null. So we simply set the left node of 57 equal to 32. And then we insert the rest of the nodes. Next, let's look at Inorder Traversal of our binary search tree. Inorder Traversal will look at the left node, then the root node, then the right node, recursively all the way through the tree. So let's step into that method. So more information on Inorder Traversal. Inorder Traversal basically goes left to right. We find the left leaf node, then the parent of the left leaf node, then we see if the right node has a left node, and then recursively go up the tree. Basically keep going left, then recursively to the parent, then right. After the traversal, the numbers returned will be in ascending order. So here's our method, Inorder Traversal, on our binary search tree class, which simply checks if the root is not null, then we can call Inorder Traversal on the root node. Otherwise there's nothing to traverse, so nothing to display. Now we're in our node class. So to traverse through the tree, we can recursively call the Inorder Traversal method. First we check if the left node is null or not. If the left node is not null, then we call Inorder Traversal. Then, after we called all the left nodes, which we'll print after we find the leaf node, then we print the root node, and then we check the right nodes, which will recursively call Inorder Traversal until we reach the end of the right nodes, and those will be printed as well here. So let's check out Inorder Traversal. So we're calling down the tree starting at 75. The left node of 75 is 57, so we call Inorder Traversal recursively. Then the left node of 57 is 32, so we call Inorder Traversal recursively. Then the left node of 32 is 7, so we call Inorder Traversal recursively. And now our left node is null because 7 is the end of our left nodes, and we simply print out 7 as our data. This node does not have right nodes, so we continue. Then we print out the root node of 7, which is 32. And then we call the right node of 32, which is 44. And 44 does not have any left node. So we print out 44 and does not have a right node either. So now we jump up to our previous call for our previous left node, 57. And we print 57. And then we check if it has a right node, which it does, is 60. And so we'll call Inorder Traversal recursively on 60. 60 does not have a left node, so we skip that. And then we print 60. And this recursively goes on until we go through the entire tree. So here are our results for Inorder Traversal, where we go left to root to right. 7, 32, 44, 57, 60, 75, 86, 90, 93, 99. Next, let's look at Preorder Traversal, which goes from the root node to the left node to the right node recursively through the tree. So here's our Preorder Traversal method on our binary tree class. It simply checks if the root is not null. If the root is not null, then it simply calls the Preorder Traversal method on the tree node class. Our root is not null in this case, so we will call Preorder Traversal on the root. Now we simply shift the order of our methods. Now we're simply printing out the root right away, and then we're looping through all the left nodes, and then we loop through all the right nodes. So as you can see, we went to the root, which is 75, then we went to the left node 57, then the next left node 32, then we went to the next left node 7, Then we went to the first available right node from the last left node, which is 44. Then we jump up to the first right node of the next last left node, which is 60. Then we go to the first right node, which is 90. And then we go to its left node, which is 86. And then we go to the remaining right nodes, which are 93 and 99. Next, we'll look at Postorder Traversal, which goes from the left node to the right node and then the root node. So we call our Postorder Traversal method on our binary tree class. The root is not null, so we call the Postorder Traversal method on the root. So now we're in our Postorder Traversal method on our tree node class. And as you can see, we start looping through the left nodes first, then we loop through the right nodes, then we'll finally print out any root nodes. So it prints out the first left node, 7, as expected. Then the right node, 44, comes through. Then the root node of those two nodes, 32, which was the previous left node, comes through. And so on, all the way up through the tree and down through the other side of the tree. So our Postorder Traversal results from left to right to root are 7, 44, 32, 60, 57, 86, 99, 93, 90, 75. The next method on our binary search tree is the find method, and we're going to look for the number 99 in our tree. So we call binarytree.find99. Here's the find method on our binary tree class. It is big O of log n base 2. We check to see if the root on the binary tree class is null. If the root is null, we simply return null. We could not find anything. Otherwise, we can call the find method on the root. So here we are at the find method of our tree node class. This method will go down the tree until it finds the number that we are looking for. Otherwise, it will return null. We do this by making a current node variable and setting it to the current node using the this keyword. So our current node is the root node, 75. Then we go down through the tree until the current node is null. So we start at 75. If the value passed in, which we're searching for 99, is equal to the current node's data, which is 75, then we return the current node. Also, if we're using softdelete on our class, then we must check if the node has been deleted, so we can ignore this node. In this case, 75 is not equal to 90, so we must check if the value is greater than the current node's data. Since 99 is greater than 75, we must look at the right node now in the tree. If it wasn't greater than 75, we would look at the left node in the tree. So we set our current node equal to the next right node, which is 90. So we come into the loop again, and 99 is greater than 90, so we must go to the next right node. The next right node is 93, so we'll come in here again. So the next right node is 99, so we'll loop through again. So our current node is now 99 in this loop, and since our value passed in is 99 and our current data is 99, we can return the node that we found. So you can see we looked for 99 and we found 99 on our binary search tree. The next method to look at on our binary search tree is the find recursive method. So we call binary tree find recursive of 99. The find recursive method on our binary tree class is big O of log n base 2. If the root is not null, then we can call the find recursive method on our tree node. Otherwise, we return null. Here's our find recursive method on our tree node class, which takes in a value. If the value is equal to the data of the current node, then we return that data, which in this case is represented by this, since we are calling this method on each individual node. If the value passed in is less than the current node's data, and the left node of the current node is not null, then we look at the left node and call find recursive of the value on that left node. Otherwise, if the value is greater than or equal to the current node's data and the right node is not null, then we call find recursive on the right node. If both the left node and the right node is null and we didn't find the data, then we simply return null. So in the case of looking for 99, the root 75 is not equal to 99. Value 99 is greater than 75, so we call recursively with 99. And now the current node that we are looking at is 90, which is not equal to 99. Then we recursively call with the value 99 on the right node of 90, which is 93. Since 99 is greater than 93, we look at the right node of 93, which is 99, and recursively call find recursive, passing in the value of 99. And so now we're looking at the node that has 99, which is equal to 99. So we simply return the current node of 99. So here's our results. We went to find the number 99 recursively, and our result we got back was the node 99. Next, let's look at deleting a leaf node. So we're going to delete the leaf node 44 on our binary search tree. So we call binary tree.remove 44. Here's our remove method on our binary tree class. It is big O of log n base 2. So we take in the data that we want to delete, which is 44. Now we want to set up our variables, which is the current node and the parent node of the current node. So we set them both to the root node, because that's the first node that we're looking for. And this allows us, once we go down the tree, to use the parent node to delete its child node. This will make sure that we maintain references in our tree. So at this point, the current node and the parent node are set to 75. We also need to keep track of which child of the parent should be removed. So we have a variable boolean isLeftChild to say, is this the left child of the node or the right child of the node? If it's true, it's the left child. If it's false, it's the right child. So now we check if the current node is equal to null, or the root node is equal to null. And in this case, we have an empty tree. There's nothing to delete, so we just return from this method. But that is not the case in our tree. Now the first thing we need to do to delete the node is to find the node. If the current node is not null, and the data of the current node is not equal to the data that we're searching for, then we continue to loop through and go down the tree until we find this data. Otherwise, if we loop through and go down the entire tree, we simply check if the current is equal to null, and then we just return from the method, because we did not find this number to delete. So first thing we do in the loop is set the current node to the parent. If the data that we're looking for is less than the current node, then we need to look at its left child. So we set the new current node to be the left node of the current node. Then we also must note that this is the left child of the parent node. Otherwise, if it's greater, then we look at the right child. We set the current to the current right child, and then we set isLeftChild to false. So since 44 is less than 75, we get the next left node. We set isLeftChild to true. Now the current node we were looking at is 57. 44 is less than 57, so we go to the left node. Now the current node that we're looking at is 32, and 44 is greater than 32, so we go to the right node. And then we set isLeftChild to false. So now we break out of the loop because our current data, 44, is equal to the data that we were looking for, which was 44. Our current node is 44, and the previous node, or its parent's node, was 32, and it is the right child, which is signified by isLeftChild is equal to false. So our current node is not equal to null, so we skip this. Now we need to check what kind of node that we found in the tree. This node has no children, it has no right child node, it has no left child node, so it is a leaf node. If the leaf node was the root node, then we simply set the root node to null. Otherwise, if it's not the root node, then we need to see which child of the parent should be deleted. So we check our isLeftChild variable, and we can see it is false. So we go to the parent, and then we set its reference to its right node, or its right child node, and we set it equal to null. And now 44 is removed from the tree, as there is no node referencing this node, and it will be cleaned up by garbage collection in C#. As you can see, the node 32 does not have a right node of 44 anymore. The node has been deleted. Now let's do a slightly more complicated operation and delete a node with one child. So let's delete the number 93. So we call our binary tree.remove method, passing in the number of 93. So here we hit our remove method on our binary tree class. We loop through and find our node. So we found the node 93. So we're looking at to delete 93. 93 has a right child, but it does not have a left child. So we skip this first section. Since it has a right child, we skip the second section. And since it does not have a left child, then we know that it only has a right child. Since the current node that we're looking at only has a right child, we must set either the left or the right child of the parent node to this right child node. If the current node was the root node, then we simply set the root node to be the right node of the current node, and so that'd be the only node. Otherwise, if it's not the root node, then we check if the current node is the left child or the right child of the parent. In this case, we are dealing with the right child because 93 is the right child of 90. So we set the right node, which is currently 93, to the right child of 93, which is 99. And so that node is now removed from the tree, and our references are connected. If we're in the case where the right node was null, so the current node would only have a left child, we set one of the parent's children nodes to be equal to the left node of this current node, just as we did with our node to be deleted that only had a right child. So we go through the same steps. We set the left node to root if we're looking at the root node. Otherwise, we got to see which child it is. If it is the left child of the parent, then we set it to the left child node of the current node. If it is the right child node of the parent, then we set it to the current node's left node as well. Next, let's look at the most complicated of the delete operations. We will delete a node with two child nodes. So in this case, I'll be deleting the number 75, our root node from the tree. So we call binary tree.remove, pass in the number 75. So here we're at our remove method again. We set up our parameters, then we look for the node in the tree. We make sure the node's not null, and now we check how many children does this current node have. So we skip this first section. The right node is not null, so we skip the second section. The left node is not null, so we skip this section. So now we've reached the area where you have a left child node and a right child node. So when both child nodes exist, we can go to the right node and then find the leaf node of the left child, as this will be the least number that is greater than the current node. It also may have a right child, so the right child will become left child of the parent of this leaf, aka the successor node. So here we're going to find the successor node, which is the least greater number of the current node. So we call our getSuccessor private method, passing in the current node 75. So here's our getSuccessor method that takes in a node of type tree node. So we set up our variables similar to before. We keep track of the parent of the successor itself, and the current node, which is the right node of the actual current node. So we must go to the right to find a number larger than the current node. And then we go down the tree from all the left nodes of that right node to find the least greater number than the current node. So here's our loop, and we loop through until the current node is null. So we're setting our parent of the successor equal to the successor, and the successor to the current node. And then each time we go through the loop, we look at the next left node until we reach the leaf node. So if the successor is not just the right node, which is not in this case, as the right node of 75 is 90, and the successor is actually 86, then we must set the left node on the parent node of the successor node to the right child node of the successor in case it has one. So here we have the parent of our successor node, and we are looking at its left child, which is currently 86, the node that we're going to move in 75's place. So we would set the left node of 90, which is the parent of 86, equal to the right node of 86, but 86 doesn't have a right child node, so it simply is set to null. So now we need to swap 86 and 75. So we set the right child of 86 to 90, which was the previous right child of 75. Then we need to set the left child node of 86 to 57, which was previously the left child node of 75. So since the current node is also the root node, we simply set the successor node equal to the root node. Otherwise, if it was not the root node, then we would check if it was the left child or the right child, go to the parent node, and then set the successor to the left child node or the right child node, respectively. A much simpler method to delete a node is to do a soft delete on the node. This avoids rearranging the tree. So let's check out soft delete. So here we call binary tree.softdelete of 93. So here's our method soft delete on our binary tree class, which takes in integer data. So it takes in the number 93. We first need to find that data, so we call the find method and pass in the number 93. So it calls our find method on our binary tree class, which will in turn call the find method on our tree node class. Once we find the node, we check if it's null. If we didn't find the node, then we wouldn't have anything to delete, so we don't delete the node. But we did find the node, it is the node 93. So we call delete on the tree node 93. Now inside of our tree node class, here's our delete method, and it simply sets the variable isDeleted equal to true. So now if we were to go into our find class or our find recursive class, when the value is equal to the current node's data is found to be true, we would also check if this node is deleted, and even if the data on the node matches the value passed in, since this node has been deleted, since isDeleted is equal to true, we will skip this node and will not be found in our tree. Our next method is smallest, which gets the smallest number in the tree. So we call binary tree.smallest. Now we're in the binary tree class, and here's our method smallest. If the root is null, then we simply return null. Otherwise, we call smallest value on our root. In this case, the root isn't null. So now we're looking at the smallest value method in our tree node class. This method recursively calls itself, and it will break when the left node is equal to null, as we found the smallest item in the tree. So the left node of the current node is 57, which is not null, so we call smallest value on this node. The left node of 57 is 32, then the left node of 32 is 7, so we continue to loop through. 7 does not have a left node, so now we found the smallest node in our tree, and we can simply return the data. As you can see, we called getSmallest and we found 7. Now let's look at the method to find the largest node in our tree. So we call binary tree.largest. It's set up in a similar manner to smallest, except for looking at all the right nodes in the tree. So we're in our binary tree class looking at our largest method. If the root is null, then we return null. Otherwise, we call largest value on our root. Now we're in our tree node class looking at our largest value method, and it loops through until it finds the last right node. So the first right node of 75 is 90, so we call largest value again using that right node. The next right node is 93. Then 99, and 99 does not have a right node, so the right node is equal to null, and we should return 99. So here you have it. We called getLargestNode, and we return 99. Our next method is used to get the number of leaf nodes in the tree. So we call binaryTree.numberOfLeafNodes. Here we're in our binary tree class. Here's our number of leaf nodes method. If the root of the binary search tree is equal to null, then we have 0 leaf nodes, so return 0. Otherwise, we call number of leaf nodes on the root. Here's our number of leaf nodes method on our tree node class. This method will recursively call itself, and it will return 1 for each leaf node that's found. And the leaf node occurs when the left node is null and the right node is null of the current node. So we set our initial count to 0 for left leaves and 0 for right leaves. So as we loop through, if our left node is not equal to null, then we recursively call this method using our left node. Also, if our right node is not null, then we recursively call this method using our right node. So as we come in here with our first node, 75, it has a left node and a right node. So we continue, set our counts to 0. Then we call this method using the left node, 57, which then 57 will call 32. 32 will call 7. But 7 does not have a right node or a left node, and so it is a leaf node, and we return 1 from this method, which brings us back to here, to leaves, and we set left leaves equal to 1. Then we check the right node of 32, which was the parent node of 7, and the right node also has no children, so we return 1, and now the right leaves is equal to 1. So we return left leaves plus right leaves. So our total from our node 32 is 2 leaf nodes on the node 32. So we set the leaves equal to 2. And that will recursively go through this, adding the left leaves to the right leaves each time until we have the total number of leaves. So the right node of 57 is 60. 60 has no right or left node, so it is a leaf node. It returns 1. So now we add 1 from the right node 60 to our current total of left nodes, which is 2, and we have 3, and we'll continue to loop through until we count up all the nodes in the tree. So we have 5 leaf nodes just as expected: 7, 44, 60, 86, and 99. So finally, let's calculate the height of the tree by calling binaryTree.height. Here's our height method on our binary tree class. If the root is null on the binary search tree, we simply return 0. Otherwise, we call the height method on our root. Here's our height method on our tree node class. And we loop through in a similar way as our number of leaf nodes method. We return 1 every time we found a leaf node. So we set our left and our right totals equal to 0 initially, and then we recursively go through each branch. So go through all the left nodes and all the right nodes until we find leaf nodes. So our first leaf node is 7, Then we look at 32's right node, which is 44, which is also a leaf node. We check if the left total is greater than the right total. If it is, we return the left total plus 1, otherwise we return the right total plus 1. In this case they're equal, and so we return the right total plus 1, which is 2. So essentially we count every single node of a single branch until we find the branch with the most nodes. And our binary search tree has a height of 4, just as we expected. The next thing to look at pertaining to binary trees is the balancing of binary trees. Some examples of self-balancing binary trees are the red-black tree and AVL trees. If you're interested in learning more about this, please subscribe to this channel. If you liked this video, please give it a like and a comment below. And thank you for watching.